First-order system response. By the end of this section, you should be able to place first-order systems into their standard form for analysis. You should be able to identify the defining parameters that make a first-order system. And you should be able to sketch the response of a first-order system experiencing a step input. We spent the first unit working on putting our systems into transfer function form or state space form and completing the modeling step of our analysis. Now we're going to properly look at the analysis portion to see how the system is going to behave given some input into it. So we're starting with a first-order system. So the general form that we're going to see first-order systems in is we're going to have an x dot term, an x term, and then some forcing function on the right-hand side. Here I'm just using x as our dependent variable, and then time, as always, is our independent variable. So in this case, we have this coefficient tau in front of the x dot term. The x has a 1 in front of it, and then we have the forcing on the right-hand side. We can always rearrange our first-order system to look like this if we have a coefficient of 1 in front of just that x term, the non-derivative term. So specifically, we're going to be looking at what happens when we have a step input into our system. So that is to say that that f of t specific for the analysis now is going to be a step function with a magnitude of b. Well, then f of t is going to be some amplitude b times the step function. Here I'm using h for the Heaviside function. So analyzing other types of inputs, that is going to be outside the scope of this section. Here we're just looking at what happens when the right-hand side is a step input. So what we want to do is, following the modeling procedure that we saw previously, we can take the Laplace transform of both sides. We're going to then assume, or we're going to take the initial condition x of 0 as 0, and then we're going to solve for our dependent variable. So again, taking the Laplace transform of the left-hand side, we'll get a tau s big X plus big X equals b over s, because the Laplace transform of the Heaviside or of the step function is 1 over s. So again, we want to isolate that dependent variable x, so we will get that x equals b over tau s squared plus s. Now, what we were doing at the beginning of the course is we can take this and we can now do the inverse Laplace transform. After we do some algebraic manipulation, we can take the inverse Laplace transform and solve for x of t. So if we do that, skipping some of the algebra steps, x of t is going to be the b, the amplitude of that step function, times quantity 1 minus e raised to the negative t over tau power. And really what this has done, since we're doing it algebraically, we have just solved every first-order equation that was in the form of tau x dot plus x equals b times the step function. This is the solution to all of them. So if we know the amplitude, if we know the value of tau, we know the value of x at all points in time, at least all positive points in time. So t equal to 0 or larger. What happens to the value of x of t at least important points in time? So let's look at 3 points in time, and we'll see what the value of x is. So we can look at when t is 0. At least for this function, we're going to find that x of 0 is 0. Well, that better be true because that was our initial condition in the system. Then we can look at what happens when t is equal to tau, that coefficient in front of the x dot term. Well, then we're going to have this 1 minus e raised to the negative 1 power, and we multiply that b, and it's going to be about equal to 0.6321 times b. So I have a value of about 63% of b when time is equal to that value tau. What tau is, we're going to talk about in a little bit, but for right now, it's just that coefficient in front of the x dot term. And we can see what happens as time gets large. As time goes to infinity, what happens to the value of x? Well, that exponential term, we're going to have e raised to a very large negative number, which is going to go towards 0. So we're going to have b times 1, which is just going to be b. So this, what we call the steady state value of x, or the value of x when time is large going towards infinity, x is going to approach b. So in this system, x is going to start at 0, and it's going to asymptotically approach the value of b as time goes forward. Now, how does this link together with what we've been working on previously in the modeling steps? Well, we were spending a lot of time developing a transfer function, so let's see how we can use that transfer function and, looking at its makeup, be able to assess what is going to happen to our dependent variable as time goes forward. So in these first order systems, we are looking at, in the electrical world, these would be RC circuits would be of first order, or in the mechanical world, spring mass damper systems where we are neglecting the mass. So if we just have a node. So less likely we're going to see systems like this mechanically, but definitely electrically. So we're interested in analyzing this because we can implement for now what I will call passive control, which is we're going to be able to tune or select the parameters of elements of our system in order to get some desired response in the system. So we could choose the spring constants, we could choose the capacitances of the capacitors, the resistances of the resistors, in such a way that our system is going to have some sort of response when it's at least affected by a step function for now. Now, when we get into Unit 3, talking about control, that's going to be active control, where we are going to be controlling what the actual input into the system is. Here, we're just selecting what the elements are that make up our system. So what we want to do is work on the transfer function for our system, and we want to put it into this standard form when we have a first order system. So we're going to start at the same place we just were, that this is the first order system that we're looking at, this tau x dot plus x. This one looks a little bit different. I have some constant a on the right hand side times f of t. And this just generalizes what we're looking at a little bit. So again, I can take the Laplace transform of both sides like I did previously. So tau sx plus x equals a times the Laplace transform of f of t, or big F. And big X, big F are going to be functions of frequency, functions of s. Now I'm going to entirely stay in the frequency domain here. So I can group the coefficients of x together, tau s plus 1 on the left-hand side. And now I want to make the transfer function this time. I don't want to do the Laplace, inverse Laplace transform. So I want to find x over f. So I can divide both sides by that tau s plus 1. So I get a transfer function. I'll just call it g, which is my output x over my input f, is going to be a over tau s plus 1. Now, if we can express our transfer function in this form, specifically with tau s in the denominator plus a 1, and we might have to do some algebra to make sure that the constant term is 1 here, but if we can identify the a and the tau, well, we've already solved every problem that looks like this. Every first order ordinary differential equation with a step input, at least, we have solved. We know what the closed form solution looks like. So we don't need to go back into the time domain because we already know how the system is going to behave. We know what at time 0 the value is going to be. We already know how to calculate the steady state value, and we're going to know a value in between. We're going to know the value when time is equal to tau. So what this lets us do is sketch the response of our system. We're not going to be able to perfectly sketch out the value of x of t at all points, but we're going to be able to sketch it at a couple of key points and get at least a general idea of what the system's response is going to look like. If we want a more exact form of the response, either we can use the closed form solution directly that we saw previously, or we're going to be simulating this in MATLAB, and it's going to fill in a lot of those gaps. And we're going to be able to compare our sketch to the more precise solution that MATLAB is using, or to the exact closed form solution. So let's look a little bit more at what is this tau that's appearing, this coefficient in front of the x dot term, and then the coefficient later in front of the s term in the denominator of our standard form. Well, tau is what we call the time constant. And as the name implies, time constant, it is going to have units of time. Typically, we're going to be working in seconds as our base unit, so that means tau is also going to have units of seconds. And in general, it's going to be a measure of how quickly our system responds to an input. A smaller tau value is going to generally be a quicker response. A larger tau is a slower response. When we're talking here specifically about a step input, tau is telling us the amount of time it's going to take for our system to reach about 63% of its steady state value. But we can have other types of inputs into first order systems that we're going to look at in later sections. So for example, if we have a periodic input into our system, like a sine or a cosine, then what tau is going to tell us is the bandwidth or the cutoff frequency of our system. So we're going to be looking at in two sections when we look at periodic inputs or harmonic inputs into our system, how the time constant is going to affect that behavior. So how do we make the sketch of our system once we can put it into this standard form? Well, again, we know those three key values that the response of the system is going to have based on the closed form solution that we found previously. So here we're going to kind of re-examine it. So we put our system into our standard form, that transfer function, so that a over tau s plus 1, we identify the value of a, we identify our time constant tau. Then we say our system is experiencing a step input with a magnitude of b. So our input, I'll call it here u of t, is going to be b times h of t, b times that Heaviside function. So things we know about the system, we're going to know that the steady state value of our system, or the value of y, I'll call our output here, as time goes to infinity, is going to be, here I'm writing it as a times b. So b, again, the amplitude of our input, and then a, the numerator, that constant in our fraction when we have our transfer function in its standard form. And we know from previous what the closed form solution is. We're really not going to be looking at the closed form solution too much when we're doing our sketches, because we, again, know that at 0, this system is going to have a value of 0. We know at steady state it's going to have a value of a times b, and we know at one time constant, then the value will be 63% of the steady state value. So with those three key features, we're going to be able to make the sketch for any first order system that we can put into standard form. And all first order systems are going to asymptotically approach the steady state value. In this case, since our steady state value is positive 10, it's larger than our initial value, we are going to asymptotically approach it from below. But we could conceivably have a steady state value that is negative or lower than our initial value, in which case we are going to asymptotically approach it from above. But they're all going to have asymptotic approaches to the steady state value when we have first order systems with a step input. So really the key parameter that determines the response of first order systems is this tau, the time constant. So let's look at a quick comparison before we go into our example of how that value of tau is going to impact the rate at which our system responds. So here we have two transfer functions in that standard form. On the left, that 10 over s plus 1. Again, that constant 1 has to be in the denominator. And on the right-hand system, 10 over 5s plus 1. So we see that on the left-hand side, our tau is 1, a 1-second time constant. And on the right, that value of tau is 5, a 5-second time constant. Now, presuming that they are both experiencing a unit step function input, so b is going to be equal to 1. Their numerators are 10, that's the a value. That means they both are going to have the same steady state value, a times b, or 10 times 1, 10. And they are both going to start at 0 because this is a system where we have a constant in the numerator, and then we have a tau s plus 1 in the denominator. And then we're going to see that at one time constant, the value of our output will be 63% of our steady state value. So let's see how the systems differ. They look generally exactly the same, but what's different in these two plots is the scale of the horizontal axis. On the left-hand system, let's see the difference. So again, we have that time constant of 1 second. And if we come up here and just look at what the value of the graph is, it's about 6.3 or so, or 63% of 10. So after 1 second, the first system has an amplitude of about 6.3. The second system with that larger time constant is going to react slower to that step input. So let's see here, at 5 seconds, it has a value of 6.3. So it reaches 6.3 later at 5 seconds on the right-hand side versus 1 second on the left-hand side. So a slower response due to that change in time constant from 1 to 5. But what they do have in common is they are both approaching that same steady state value of 10. They're both approaching it asymptotically from below. They're both starting at 0. And it's true, they're both at 63% of 10 after one time constant. But the difference is, what is that time constant?